Okay, let's break down the mechanics of this crane. So we have there's a cylinder here. So this cylinder, revolute joint on each end, prismatic joint in the middle, raises and lowers the boom. The boom is that long diagonal piece. Then this is also extending. So we'll have prismatic joint there. And this goes all the way and connects with a revolute joint on the bottom. So we have those 2 degrees of freedom. And then what we also have is a winch here. So a winch is a spool that the cable is wrapped around, and it kind of operates separately from the other 2, depending on if you want to raise and lower this beam right here. So the winch will unroll the cable to raise and lower the beam. Then the bottom cylinder will raise and lower the boom, and the top cylinder will extend the boom. It's not really a cylinder, it's a linear actuator, but they both behave as prismatic joints. So now we need to label all of the links and joints on here. Okay, so we have the 2 prismatic joints, and then we've got revolute joint here, 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 and the way this cable acts is like a revolute joint. So we've got that. Also acts like one up there. And then this sort of extends. So now let's draw in. So we've got a vector here. And we're going to assume that the base is parked. So we can work out the kinematics of this in 2 dimensions, assuming no swiveling of the cab. Now, in real life, the cab could swivel, but it doesn't swivel relative to the whole machine part of the crane. So the cab and the rest of these extenders and stuff are all connected. So no matter which way the cab points, the connections are still going to be at the same position relative to it. So basically, we'll just say that this is ground. That this isn't going anywhere, and then everything else is connected to it. So if that is ground, then that means that this whole piece is also ground. So that doesn't move. So let's put on the rest of our vectors then. We'll have a vector here. We'll have one here. And then the winch is a circle, so we'll have a vector that goes on it. And we have the cable, a vector there. We'll have the bottom cylinder being a vector, and then we'll have one vector that goes along the boom there, another vector that goes to where it starts extending, and then another vector to where it finishes extending. Now this middle vector right here, we didn't necessarily have to put that. We could have connected the top all the way to the bottom one. But for the purposes of plotting, it just helps us to know where the cylinder actually starts extending and where the joint is. So it's okay to put both of those. So now we just need to label each of these. So we'll say the ground, this part here is R1, and then R2, R3, R4, R5, R6, R7, and down here is a little hard to see, so I'm going to erase that and redraw it bigger. Okay, so then that one is R8, and then this one down here is R9. So we've got all of the vectors, and now we can figure out how many loops there need to be. So here there are going to be 2 loops. We can see the bottom loop here and the top loop here. Now notice that the hanging part of a cable, R6, is not part of either of the loops. That's because it's not a loop, it just hangs. So that part will have to be treated separately. So we'll do the vector loop analysis for these 2 loops that'll use all of the R's except for R6. And then separately, we'll have to do just a vector analysis, not a vector loop analysis, to calculate R6. So let's start by drawing or writing down the vectors that make these loops. So for the top loop, let's go around this loop counterclockwise. So first, let's establish a coordinate frame. Say our coordinate frame is X goes here, Y goes up. So now writing out the loop equations, if we start at this point, then we'll have R9 plus R8 plus R7 minus, because we're going against, R5 minus R4 minus R2, and that equals 0 because we ended in the same place we started. So now the bottom loop, this one there are a lot fewer. We just have R1, R2, and R3. So let's go around this loop also counterclockwise. R1 plus R2 minus R3 equals 0. So that's a much smaller loop. Now we can split this up into position scalars and then figure out knowns, unknowns, inputs, constraints. We'll see what variables are known. Those are the things that don't change. What are unknown? Things that do change. And what are inputs? Those are the actuators. So looking at that, we have 2 inputs. One is the boom raising and lowering cylinder. That would be R3. And the other one is the extending of the boom, which is R5. So R5 would go from 0 when it's fully contracted to some number when it's completely extended. So then for the knowns, that would be all the values that don't change. So looking at that, let's go through the R values. So all of the R values are constant except for the 2 cylinders and the hanging part of the cable and the not hanging part of the cable. So anything that's like a physical structure, it is a known value if it doesn't extend. So that would be R1, R2, R4, R8, and R9. Because the length of the cable can change, so R6 and 7 are going to be unknowns. So we'll put those in there. We're actually not going to talk about R6 until, because is not part of the vector loop, so we'll treat that later. So we have R7 as an unknown. And then for angles, we know all of the angles that are connected to the ground, so that would be theta 1, theta 8, theta 9. And then unknown angles would be all of the other ones. So theta 2, theta 3, theta 4, theta 5, theta 7. Okay, now constraints. We can see that in this picture, R2, R4, and R5 are all collinear. So R5, R4, R2, they all point in the same direction. So we know that since they all point in the same direction, they all have the same angle. So that will actually kind of help eliminate some of these unknowns because these are going to get calculated when theta 2 gets calculated. So we'll use that constraint to eliminate some of the unknowns. And then now we have 4 unknowns. So we'd need 4 equations. Since we have 2 loops, we'll get 2 equations from each loop, an x and a y, and that will give us the 2 equations we need. So for the top loop, we'll have x top and y top. And we'll put these in the most simplified form possible. So looking at the top loop, we can see that R9 and R8 only point in the x direction. So we'll have R9 and R8 like that. And then we'll have the cosine component of all of the other R vectors. But remember from our constraints, theta 2, theta 5, and theta 4 are all equal. So we can simplify this part of the equation. Now for the y component, R8 and R9 won't be there because they only point in the x direction, but we'll get the sine components of all of those other r's. And now for the bottom loop, we have R1 points in x and y, and R2 and R3 also do. So those will all have cosines for x and sines for y. So now that we've got these position scalar equations, we need to be able to solve the loop. So you can solve that using Newton's method because there's no easy algebraic solution for this. So you could solve it numerically using Newton's method. For that, you'd need to find the Jacobian, which is the partial derivative matrix. So there's a way to do that using velocity, but if you haven't learned velocity, then we can do this method. So for velocity, click the link. For doing it using the partial derivative Jacobian method, then that's what this video will do. So we need to find the Jacobian. Now, Jacobian is going to have one row for every position scalar equation. So we'll have 4 rows, each corresponding to x top, y top, x bottom, y bottom. And then it will have however many columns of unknowns. So there are also 4 unknowns, theta 2, theta 3, theta 7, and R7. So we'll set up the Jacobian with columns corresponding to theta 2, theta 3, theta 7, R7. So now we just need to fill out this matrix of partial derivatives. So it'll have 16 things in it because it's 4 by 4. Some of those things might be 0, and if they are, that's okay. It will make our math easier. So if we want to see taking the partial derivatives of the xt equation, we can see what is the partial derivative with respect to theta 2. Well, derivative of cosine is minus sine. There's already a minus sign in front. So we'll just have sine of theta 2, and it will be times all of those r's that are in parentheses. So R2 plus R4 plus R5 sine theta 2. And then for the theta 3 derivative, that doesn't show up. There's no theta 3 term. So we'll have a 0. And then theta 7 derivative, we'll have derivative of cosine is minus sine. So we'll have minus R7 S7. And then the derivative for the r, because remember the r changes as well. Derivative of r is with respect to theta, it doesn't have a derivative. So that will just be times, it would just be times C7. So now for the second row, let's look at the theta2 derivative. So derivative of sine is cosine, but there's already a minus sign in front. So we'll have minus R2 plus R4 plus R5 times cosine theta2. And again, nothing for theta3. And then we'll have an R7, C7, and S7. So now for the bottom loop. R1, theta1, neither of those change with time. So those derivatives will just be 0. Now, if we need partial derivative with respect to theta2, here, then derivative of cosine is minus sine, so we'll have minus R2, S2. And then for theta3, we'll have minus R3, S3, but there's already a minus there, so we'll get rid of that, and it will be a plus R3, S3. Then there's nothing with theta7 or R7, so these columns will just be 0. Now finally for the y equation, no partial derivative for the theta1 stuff. Now for theta2, we'll have R2, C2. For theta3, we'll have negative R3, C3, and then again 0 and 0 for theta7 and R7. So this is the Jacobian matrix that you would be able to use in Newton's method to solve the system numerically. Now, finally, we've solved the two loops, but we haven't solved the hanging part of the crane. So that R6, theta6, we need to get that vector. So the way that this crane operates is kind of interesting. As the boom extends and retracts, then the cable rolls and unrolls to keep the beam at the same height. So then that hanging part of the cable would change there. The bottom position would be the same. The top position would be whatever position that the boom has gotten to. So there will be a couple different cases here. We know that theta6 equals negative 90 degrees. Always, it'll hang straight down because of gravity. But R6 could be different things in different situations. So we know that if the boom extends, let's just label these 2 points. Say this is P1. Actually, we'll call it PB for bottom. And then up here, we'll label this as PT for top. So if the boom is extending, the cable is going to unroll to keep the PB at the same height. So in that case, R6 is just going to equal P top minus P bottom. So that is if boom extends. So this in your code would kind of be an if statement. So then the other case is when the cylinder, the R3 cylinder is extending or retracting. In that case, the winch locks into place, and so the cable can't extend anymore, but the hanging part of the cable and the R7 diagonal part of the cable are going to be a constant. So something that would look something like R6 plus R7 equals constant. Let's call this constant L. So that would be the cable's locked at a certain length, but which length half is in R7 and which length half is in R6 can change. So here, we just rearrange that equation. We'll have R6 equals L minus R7. And that is going to be if cylinder extends. which would be boom raises. So to interpret that, this would be R3 moves, and the extending part of the boom would be R5 moves. So then there's a third case, which is when neither R3 nor R5 are moving, but the winch is going to unroll to lower the cable into the ground. So in that case, R6 is going to be whatever its starting point was, plus the angle that the winch turns through, theta 8, times its radius, which is R8. So R8, theta 8, if winch unrolls. So that would be theta 8 moves. So 3 different possibilities. So in your code to calculate this, you'd need an if statement to figure out what is actually happening. So now that we've got all this math done, let's look at a Matlab simulation. Here you can see as the boom of the crane extends, the winch unrolls to keep the beam at the same height. Then it locks into place as the cylinder raises up the beam. And then it stays locked into place as the base swivels around to set the beam in a new location. And then the winch unrolls to extend the cable to lower the beam into the ground.